In this video, we'll be learning about Euclidean algorithm. As we know that we want to find the greatest common divisor of two integers, and we can find out the greatest common divisor of two integers by listing all their positive divisor and choosing the largest one which is common to both. But that process is really long. So to find a more efficient algorithm, we have now this Euclidean algorithm. And to start this algorithm, let us consider the two integers. So I'm considering a and b. These be two integers, and I'm also considering that a is greater than or equal to b is strictly greater than 0. So here I'm considering that b is not equal to 0 and it is a positive integer. And also noticing that we know that GCD of absolute value of a and absolute value of b, this is same as the greatest common divisor of a and b, because whenever we consider the positive divisor of these numbers, these are same as this if a and b are positive, and we always select GCD as the greatest among the all positive divisors. Now as we said that a is greater than or equal to b, so the first step is to apply the division algorithm. So let us write the first step, and here I write apply division algorithm. Now when we apply the division algorithm, so in my last video I have talked about division algorithm and we have also proved that, and we have also talked about the existence of the quotient and the remainder. So here I can have this expression a is q1 into b plus the remainder r1, and the condition on the remainder is this, that it lies between 0 less than or equal to r1 strictly less than b. So for the proof of the division algorithm, you can watch the previous video. I have added the link in the description. And now there are two possibilities, that if the remainder is equal to 0, in that case we can simply say that b divide a, because we can write a is a multiple of b, q1 into b. And since b divide a, so from here we can directly write that the GCD of a and b, this is b. And when r1 is not equal to 0, in this case when remainder is not equal to 0, so we want to divide b by r1, and we consider this as the second step, and we want to produce, so there exists quotient q2 and the remainder r2 such that b is equal to q2 into r1, because we are dividing b by r1, so this is the quotient, and plus the another remainder r2. Now the condition on r2 is that it lies between 0, equality included, and this is the divisor in this case, so this is strictly less than r1. And we again check the similar manner, if r2 is equal to 0, in this case we say that b is equal to q2 into r1, and we say r1 divides b, and obviously r1 divides a, because we can see that a was q1 into b plus r1. So here we already see that q1 b value is q2 into r1 plus r1. So we can see that r1 can be common out from all the expressions. So this is q1 q2 plus 1. So r1 will definitely divide a and b both, and hence r1 can be taken as the greatest common divisor of a and b both. But if not, that r2 is not equal to 0. So suppose that remainder is not equal to 0. In this case again repeat the process. So when we repeat the process, this is what we mean by Euclid algorithm. We have system of equation a is equal to q1 into b plus r1. In this case remainder was not 0, so I processed, and then I have divided b by r1, so let me call quotient q2 plus r2, and in this case this was the condition for the remainder, and I said r2 is not equal to 0, so this division should be further carried out. So this is q3 r2 plus r3, and this means r3 is strictly less than r2, and we continue like this, and we get rn minus 2 equal to qn into rn minus 1 plus rn, and here this remainder rnth remainder is less than rn minus 1, and then I can write rn minus 1 is same as qn plus 1 into rn plus the last remainder as 0. So this process will be finite. So we say that this process is finite, or we say that this decreasing sequence will terminate, because we are talking about integer. So it cannot contain more than b integers, because we have started initially with the division of the b integers, and division means it's a repeated subtraction, so it cannot contain more than b integers, and hence it has to be finite. So that is why I have ended this process after a finite number of steps, and we say that GCD of a and b is equal to rn, the last remainder that we have started. And to justify this statement star, what we have used is that to find the GCD of a and b, I have used the GCD of b and r1, and again r1 and r2, and so on, rn minus 2, Rn minus 1 and Rn minus 1 to Rn. So now I want to prove a lemma which justify our this star statement that why the GCD of A and B is equal to Rn. So what we need to prove in the lemma is that if A is equal to QB plus R, so this is the statement that we have started. In that case, the GCD of A and B, this is same as GCD of B and R. So if I can show that GCD of these two integer is same as the GCD of these two integer, from the previous process, now our statement the star is justified. Now let us prove that this lemma with the given condition. So in this given condition, we have also taken let D is the GCD of A and B. Okay, so let us consider D as the GCD of A and B, and in this case D divide A and D divide B. And if we look together, we can always take the linear combination of these two integers, and in this case to take the linear combination from this expression, if you see that this is A minus Q times B equal to R. So I take now this linear combination A minus Q times B, or I can simply write D divides R. So I can say that D is a common divisor of both B and R also, because I have started D as a common divisor of A and B, but I have concluded now that D is a common divisor of B and R. So now let us consider that if C is any other divisor, if C is any arbitrary divisor of B and R, and as C is the divisor of B and R, so I can take the linear combination of these two, so I can write C divides QB plus R, and that implies C divide A. So this means that C is a common divisor of A and B. So C is a common divisor of A and B, but we know that A and B have GCD as D, so obviously we can say that C is always less than or equal to D, and hence we can show that GCD of A and B is same as GCD of B and R, and this is exactly the same GCD, and hence using this fact and based on this star equation I have applied Euclidean algorithm. Now let's understand this by an example also. In this example, I want to find GCD of 123783054. So I know that this number is now larger than this number. So keep this number on the left and keep this number on the right, 3058. Now choose the appropriate quotient. So this is 4 and the remainder, that is 162. We can see that the remainder is not equal to 0. So repeat this process, 3054, that is actually the B. So here this is Q, this is B, and here this was remainder. So now I want to keep B on the left hand side and I want to divide this by the remainder, and here I got 18 plus now the remainder is 138. Repeat this process, 162, this is 1 into 138 plus now the remainder is 24. Repeat this process, 138, so this is 24 into 5 times plus the remainder is 18. And so I'll keep 8 on this side, dividing by 18, this is 1 into 6, and then I get 18 is 3 into 6 plus 0. So you can see that this process is finite, it has terminated. So we can see that greatest common divisor of 123783054 is the last remainder, that is 6. So this is the greatest common divisor of these two numbers. Now this process of Euclidean algorithm does not tell us how to find the x and y. And what were x and y? If I want to write D as ax plus by, where D is the GCD of A and B. So we have used that whenever D is the GCD of A and B, that can be written as a linear combination of x and y, where x and y belongs to integer. Now to search for this x and y, what I need to do is I need to follow back the step. So now let's start immediately from the last remainder step. So I write 6 equal to 24 minus 1 into 18. So this is the last step that I have carried here. And now keep on writing the last remainder. So you can see the last remainder is 18. So this is 24 minus, keep this 1 as it is, and replace 18. So that is 138 minus 5 into 24. Now club this 24 with this 24. So this is minus 1 into 138. And then we got this minus 1 and minus 1, this is plus 5 and 1 here. So this is 6 into 24. Now replace this 24 here. So this gives me minus 1 into 138 plus 6 into 162 minus 1 into 138. So that gives me, now again club these value 138 and 138. So this will give me 6 into 162 minus 6, and then we got a minus 1 here. So this is minus 7 into 138. And now again I want to write down the remainder 138. So take out the values from this expression. So this is 6 into 162 minus 7 into, replacing this 138 from the left expression, so that is 3054 minus 18 into 162. So this gives me minus 7 into 3054. Now multiplying minus 7 minus 18 and adding this into plus 6, I will get this as plus 132 into 162. So this value is same. Now let's look at the last remainder, that is 162. So I also want to now replace 162 in my last step of the back step process. So this is 132 into 12378 minus 4 into 3054. Now clubbing these two and looking at this expression, I will write this one as 132 into 12378 plus minus 535 multiplied by 3054. So now these are the integers a and b which is given to us. This was a and this is b, and this is the value for x and this is the value for y. So these are the integer and we got ax plus by. So from the back substitution we can always find what is the value for x and y in this expression. The French mathematician Gabriel Lemay proved that the number of steps required in Euclidean algorithm is at most 5 times the number of digits in the smaller integer. In my last example, we have considered a is 1, 2, 3, 7, 8. This was the number a. And the number b that I've considered is 3059. So this is another integer that I've considered here. And we can see that in b we have 4 digits. So this means in the finding the GCD of these two numbers, we can take at most 5 times this number of digits, that is at most 20 steps. So we can say that number of divisions that we have applied in Euclidean algorithm cannot exceed 20. And in my previous example, we have seen that we have only 6 division steps. But the question is how to reduce this computation time. And the number of steps in Euclidean algorithm can be reduced by selecting the remainder rk plus 1 such that absolute value of rk plus 1 is strictly less than rk by 2. Or by working with the least absolute remainder in the division. So now in the same question, if I want to look the same question again, we have seen earlier we have spent 6 iteration, and now let us look at here again. So this is remainder was in first remainder was 162, and then I can have 3054. This is same as 19 times 162 and keep the remainder as minus 24. So this is same as 162 equal to 7 into 24 minus 6. And I can have 24 equal to minus 4 into minus 6 plus 0. So now you can see that there are only 4 steps. As we see, this last value is minus 6. So select the greatest common divisor as the positive counterpart of that. So select this remainder as plus 6.